Yes, so good afternoon, yeah, to everyone. Good morning, yeah, in some other part of the world, yeah, as I wrote, yeah. And the background picture you see here, well, I already told it, but many people were not yet present, yeah, is a view, yeah, of the Himalaya from Aries Observatory in Devastal, just to bring to us some hopes that very soon, yeah, we'll be able to join the observatories again, yeah. Yeah, so the main subject, yeah, of the lecture today that you could see on the YouTube video, yeah, referred to, well, present interferometers over the world, like the VLTI, Shara, Keck interferometer, yeah. And you have seen that uh, in those interferometers, yeah, people were using delay lines, yeah, rather than when we did, you know, our experiment with the two-hole Young's screen, where we had no delay lines, and in fact we didn't need any delay line because our eye, yeah, was acting as a converging lens, making sure that the length of all the rays and coming to the same point in our retina, was just about the same, yeah. And it was the same, yeah, for Michelson when he proceeded with the first measurement of diameters of Galilean satellites, or measuring the diameter of the disk of stars. Yeah, he put a beam with two mirrors, yeah, at the edges, yeah, over the 2.5-meter main mirror, so that he didn't use either, and didn't need, yeah, delay lines. Yeah, so the first time people used the delay lines with the two independent telescopes, yeah, was by Professor Labéry, yeah. Well, I think it was around 1975, yeah, so a long time ago. And you have seen in the lecture, you know, the first images of Vega showing the airy disk with fringes, yeah, across the airy disk, from which you could measure visibility, the contrast of the fringes, and derive, yeah, a good estimate, yeah, for the stellar diameter, yeah. Then you have seen that at the end, yeah, of lecture number 6, yeah. So on the YouTube video, that we were, well, approaching, yeah, the demonstration of the first theorem, fundamental theorem. I should say the second theorem, because the first one has been the Van Sittert, yeah, and Zernike theorem, yeah. And so this will be the subject of the next lecture, yeah. Today, what I would like to do with you is just to show you, to come back, yeah, to the Zernike-Van Sittert theorem, yeah, and well, to present an independent demonstration, yeah, which will enable people, yeah, to better understand, yeah, what's going on, yeah, what does represent physically the complex degree of mutual coherence, yeah. And well, I had the whole week, yeah, to think about a new approach, yeah, and I will share with you, yeah, what came out, yeah. So I will share my screen. And here, so can you see the screen now? Hello, hello?
Yes, Sean, you see.
Yeah, you can see, yeah, yeah. So well, the subject, yeah, of my presentation now is an independent demonstration, yeah, of the Zernike-Van Sittert theorem, yeah. Just to show you, you know, how, well, more intuition, yeah, can be put into this approach, yeah. So what is shown here, yeah, so we just take the laser, yeah, is the young screen, yeah, with two pinhole aperture here and there, yeah. And then here you have the observer screen here, yeah. And here is a particular point, yeah, in the observer screen. And what we see here is that the length of this light path, yeah, is a bit shorter than the length of this other light path, yeah. And the difference is c times tau, where tau is a time delay between the arrivals, yeah, of the photons from the two holes, yeah, to that point in the screen. Yeah. Now, star number 1, yeah, is a star along the line of sight which is perfectly perpendicular to the Young screen and to the observer screen. And as we have seen, yeah, in the Young's experiment, yeah, it gives rise, yeah, to a series of fringes, yeah, and these are the blue fringes that you see here, yeah. Now, star number 2, yeah, well, should be considered, you know, as an infinitesimally small source element, yeah, which could, be part, yeah, of a bigger extended source, yeah. And you see that its coordinate, yeah, is zeta equals 0. Zeta is an angle measured in the horizontal plane here, yeah, in the horizontal plane, yeah. So the angle zeta here is the angle, yeah, between these two lines. So star number 3 is still this coordinate zeta equal to 0, yeah, but eta is different from 0, so it's just below, yeah. So eta is an angle, as you see here, in the vertical plane, yeah, so perpendicular to the horizontal one, yeah. And what would you expect, yeah, from star 3 is of course still a series of fringes in the observer screen, yeah. And well, how will these fringes appear, yeah? Well, because the star 3 is just below star 1, yeah, it's a up and down motion, yeah. So in fact, the fringes, yeah, will be exactly like the blue ones, yeah, but they will just move up and down, yeah, which means that they will reinforce, yeah, the brightness, yeah, of the blue fringes, yeah. So any point source element, yeah, located, yeah, on this direction will contribute, yeah, to enhance the blue fringes that you see in the observer screen, yeah. So this is interesting, yeah. Okay, now star number 2, which is represented as a red dot, yeah, is a star located in the horizontal plane, yeah, which means that eta is also equal to 0, but zeta has different values, yeah, from 0, yeah. And what will happen in the observer screen? Well, it's obvious, yeah. If the star is being shifted by the angle zeta, well, the fringes, yeah, will also appear to be shifted by the same angle zeta in the observer plane, yeah. Yeah, this is very intuitive, yeah. And this is what you see here. The red fringes here are slightly moved aside, yeah. But their periodicity is exactly the same as the periodicity of the blue fringes, yeah. And so, well, you could say, okay, if I have an extended source here, yeah, well, I should consider all the small, infinitely small elements, yeah, and just put in the observer plane, yeah, the resulting fringes, okay? Now I will just shift, yeah, to a small simulation, which is here, yeah? So what I've represented here, yeah? Well, first, this is a small disk you see on the top, yeah? Circular disk, yeah? Which is seen from the side, yeah? And C is the center of this stellar disk. And if I calculate, yeah, the fringes, yeah, in the, oh, maybe I need to, yeah. If I just, so we assume that the baseline, yeah, is oriented along this direction, yeah, along the x-axis, yeah. Now we are supposed to observe, yeah, a star which is represented as a stellar disk, and the dot C represents an infinitesimally small surface element of that star, yeah. And so what we see in the observer screen, yeah, well, is a series of fringes, yeah, as expected for quasi-monochromatic light, okay? Now, what I will show, so it's a small video. In a moment, yeah, we will be shifting the point C, the black dot, yeah, up and down. Well, it didn't take my, yeah, now it will start, yeah. So you will see in a moment, yeah, this small dot, yeah, will shift up and down. So we see it from the top, now from the edge. And while moving, yeah, this small dark element, what we see here is that the fringes, yeah, are just moving up and down. They are just reinforcing, you know, the original fringes that you are seeing. Yeah. So in fact, what we should do, we should co-add, yeah, all those fringes, but which are the same. Yeah. So it will be a very big reinforcement, yeah, of the fringes, yeah, shown from the central part. Yeah. Now we are moving now laterally, yeah. So east-west, yeah, along the zeta direction, yeah. And of course, as I said before, the fringes now will move, yeah, from the left to the right and from the right to the left, yeah. So this will bring, yeah, well, a smearing effect, yeah, of the original fringes that you are seeing, yeah. But still, the periodicity is exactly the same, yeah. So, well, finally, yeah, what will be the result is that you should co-add, yeah, all those fringes to see the resulting one, yeah, from all the infinitely small space surface elements, yeah, of the star. Okay, now I move to the next presentation. And in this presentation, yeah, what is seen, yeah, is a superposition, yeah, of about 10 series of fringes, yeah, corresponding to the motion of C as a function of zeta, yeah. Okay, so I just start the video. So you see this superposition from many different lines of sight, yeah, and you see that they are shifted, yeah, with respect to each other, of course, yeah. Now, one by one, yeah, we will remove fringes, yeah, from the different source element. So here we start. We are just taking away fringes, yeah, one by one. Yeah. And the only one which will remain, yeah, is the original one, yeah, due to the central part, yeah, of the disk, yeah. So this is the one. And now, what I will show next here is a co-addition, yeah, of the 10 series of fringes that you've seen, yeah. And what you see is that, well, the contrast, the visibility, yeah, of that resulting fringe is less than the original one, yeah. And well, as we have seen, yeah, before, it should then be possible, yeah, to measure the visibility and the module of the complex degree of mutual coherence. Now, I will show you. So I just go this. I will move away. I prepare a PDF document, which is here. I double click on it. Yeah, here it is. So I've just prepared, yeah, a PDF document entitled, yeah, the Zernike-Van Sitter Theorem Revisited, yeah, and abstract is the Zernike-Van Sitter Theorem, a more intuitive approach, yeah. And well, I've just demonstrated, yeah, with some equations or illustrated with equations what I showed you, yeah, on the video, yeah. So first of all, yeah, we say, okay, the electric field, yeah, in the observer plane, yeah, is a superposition, yeah, of two series of waves coming from the two independent holes, yeah, from the two holes of the interferometer, but one reaching a hole 2 as a delay, yeah. Then, as I wrote here, yeah, from equation 17, the lecture notes, yeah, we had the relation that this quantity x is the position of the fringes, yeah, in the observer screen times the baseline divided by the distance between the observer screen and the Young screen is equal, yeah, we wrote then n times lambda, yeah. So this is the difference in length, yeah, between the two light rays. And this is also equal to c light velocity times the time delay between the arrival times, yeah, of the two beams, yeah. Now I try to move this a little bit up. So what we do then, yeah, we calculate, yeah, what is the intensity in the screen, and it is the average, yeah, of this product, yeah, of the electric fields. Then we replace equation 1 in equation 3, and well, what we find, yeah, is that it is just well, the relation, yeah, we obtained before, yeah, it's a sinusoidal variation, yeah, shown in the observer screen, and where u is a angular space frequency, yeah, defined by the ratio between the baseline and the wavelengths, yeah, of quasi-monochromatic light. Yeah. Then here is a continuation, yeah, of what I've shown. Yeah. I just said this is very important. Yeah, is that all the source elements, yeah, being located, yeah, at the same value of eta, yeah, well, will get superimposed to each other and will reinforce contrast. Yeah. And so, well, this is just a continuation. So I don't want to make the demonstration now repeat it here with the words. It's better that I will share the document with you, and very peacefully, yeah, you will have a look at it, yeah. But what is very nice, so I go here to this page, but it takes time for the screen to be refreshed. But there are 4 pages in total. But what you would find is that finally we see appearing, yeah, in this demonstration naturally, yeah, the Fourier transform, yeah, of the intensity of the source, yeah, in the observer screen. So I think this will help, you know, some of you to. Well, I just try to find out. Well, it doesn't move. This is the page number 2. It doesn't want to take page number 3, but it doesn't matter, yeah? So I will just end now my presentation here, come back to you. So I'll share the document, yeah? Well, probably tomorrow I'll send a PDF file, yeah, to Prakash to put it, yeah, on the forum. And you will see as a finally understanding, yeah, this complex degree of mutual coherence, yeah, is very intuitive, yeah? It's just the resulting fact of the following thing. When you observe with an interferometer, you have a baseline. Yeah. Now, when you take a source element, yeah, on an extended object, you get a series of fringes. Yeah. Now you should remember that all the surface elements, yeah, located, yeah, on the same vertical line, which means corresponding, yeah, to the same value of the angle eta, yeah, will just reinforce, yeah, the interference lines that you are seeing, the fringes, yeah, due to one surface element. Yeah. And now when you take the surface element just located, well, along the x direction, it means which has zeta value different from 0, yeah, you still create, yeah, a series of fringes, yeah, and all the elements, yeah, on the same line will just reinforce, yeah, the fringes due to a single surface element, yeah. But of course, yeah, at the different values of zeta, the length, yeah, of these surface elements will not be the same. So you will get, yeah, well, a mixture of fringes, all having the same periodicity, but shifted, yeah, in zeta, shifted laterally, yeah. And well, the result will be still, yeah, fringes, yeah, but with a reduced contrast, yeah, reduced visibility, from which, yeah, you will get information on the structure of the source, yeah, but only along the zeta direction, yeah, perpendicularly, yeah, to the, well, no, in fact, parallelly, yeah, to the orientation of the baseline. Yeah. Okay, so I'll end, yeah, today's presentation here, and would like to hear from you, yeah, questions, yeah, related, yeah, to lecture number 6, yeah, or to the previous ones.
Okay, thank you, John. Okay, I'll set it so that you guys can mute yourself and ask a question. So whoever has a question can now unmute themselves and ask.
Yeah, so
Go ahead,
Suhita
Suhita.
has raised her hand.
Are you able to unmute yourself? Sorry, go ahead. I think I muted you accidentally. Try again. Suhita, can you try to unmute yourself again? Yeah.
Can you hear me?
Yes, we hear you very well.
Thank you, sir, for such lucid presentation. I have a question from previous talks. To find the wavelength for Gaussian monochromatic light with wavelengths lambda plus minus delta lambda of the wave groups, we have the wavelength lambda square by delta lambda, where delta lambda is the width of the band, is the bandwidth or half of bandwidth. I am confused with this. Actually, in lecture notes, it is written that lambda plus delta lambda, and then the resulting wavelength is lambda square by delta lambda. So it becomes lambda square by half of bandwidth.
I see. Yes, so Suhita, well, just to give the right answer, yeah, what I propose, yeah, I left later a look, yeah, at the lecture notes, yeah, and make sure, you know, that you get the correct answer, yeah. I cannot, you know, just by, you know, by remembrance, no, well, it's nu plus or minus delta nu, I think, yeah, yeah. So I think that the total bandwidth then should be twice, yeah, delta nu, but I'm not sure, I should check. And I'll put my answer on the forum. Okay for you?
Sir. Okay, sir. And I also want to know how the expression lambda square by delta lambda comes from.
Oh, yes. So that one is easy, yeah? You know that nu is equal to c divided by lambda, right? Now, if we calculate delta nu, it will be equal to minus c divided by lambda square times delta lambda, right? Can you hear me?
Yes, sir, but how it comes?
Yeah, now you agree that the effective, well, the coherence length, yeah, the coherence length, yeah, that I would call lambda f effective, yeah, effective length, is equal to c divided by delta nu. You see?
Oh, yeah.
Yeah, because you see, lambda is equal to c divided by nu. So the coherence length will be equal to c divided by delta nu, which is the frequency, yeah, the low frequency of the beat phenomenon, you see? And then you replace delta nu, yeah, by what we said, yeah, which is minus c delta lambda divided by lambda square, yeah? And you'll find exactly the answer, yeah? You see?
Yes, sir.
Yeah, maybe I'll put this also on the forum, yeah, just to make sure that everybody got it right, yeah? So how to get the expression of the coherence length, yeah? which is lambda squared divided by delta lambda. Yeah.
Thank you, sir.
Yeah, with pleasure. Very nice to hear you. Yes, so do we have another
Yes,
question?
Saraswati, can you unmute yourself and ask a question? Go ahead. We don't hear you. I can see your mic is unmuted. There might be some problem with the microphone.
Yeah, in case you have difficulties, yeah, with audio, just write your question, yeah, on
Yes, in the chat.
In the chat, yeah.
So in the chat window, there's a question. I think it's about some derivation.
So just have a look.
By Zhenghui.
Okay, there is already some reply to one question, yeah, well, the question was by Zhenghui Zhu, yeah, and I see there is already a reply from Vishnu Huni, yeah. Thank you, who is very often, yeah, intervening, yeah, in the forum. Very good.
Yeah.
Okay, so in the first slide that we saw today, we have a Young's experiment setup. We have 3 stars, and we are considering 2 sets of fringes. Yes. So, yeah, maybe I come back here to this open board. I will share my screen again, yeah, and try to get back to documents. Now, I see this one. The 3 stars. Yeah. So I come back to this picture, yeah, which you will see is extremely helpful. Yeah. So just think that you have a very extended source. Yeah. Very extended source. Yeah. Very extended one. Yeah. And
Sure.
well,
Sorry to interrupt. Would you like to hear the complete question? She has just typed the rest of the question.
Yeah. So
Yeah,
so
I'll read it out. It just says, how do we, so in that particular setup, how do we differentiate between the fringes by the different stars? How do we get the positional information about the sources?
Yeah. So, yeah, we should think, yeah, that this is a very extended object source, yeah, and that star 1, star 2, and star 3 just represent, you know, infinitesimally small surface elements, yeah, of the source, yeah. So then it's very easy, yeah, if we have a quasi-monochromatic light, yeah, and that we make sure that the time delay between the arrivals, yeah, of the light beams on the observer screen, yeah, is less than the coherence time, yeah. We know that star 1, yeah, so the surface element number 1, if you want, yeah, will give rise to a series of fringes, yeah, in blue, marked in blue, yeah. Now, star 3, so it's a surface element located just below, yeah. So we see that eta, this angle in the vertical plane, yeah, is different from 0, yeah, represent another surface element. And what we know is that it also gives rise, yeah, to a series of blue fringes, yeah, which are perfectly positioned, yeah, over the fringes due to surface element number 1, Yeah, so it's just a reinforcement, yeah, of the blue fringes, yeah, which means that when we look, yeah, at those fringes, yeah, we only get information. They only get information, yeah, about the integrated, yeah, intensity of the extended star, yeah, along the vertical direction, yeah. So if you have a baseline, yeah, in that direction, yeah, well, the interferometer will just give you information, yeah, about the integrated light, yeah, of the source, yeah, over a direction which is perpendicular to the baseline, yeah. Okay, but if you consider a surface element, yeah, set at another location, yeah, in the horizontal plane, so you see that the angle zeta is not 0, yeah. What happens? Well, this is just natural, yeah. In the observer plane, you expect that the fringes will be moved, yeah, with respect, yeah, to that center in the Young screen, yeah, by an angle zeta, the same angle as here, yeah. So the angle which separates, yeah, these blue and red surface elements is exactly the same as the angle separating one blue and one red fringes, yeah, measured, yeah, from the center of in the Young screen, yeah. Yeah. So finally, we get, yeah, many superimposed, yeah, fringes in the observer plane, and we know that it will only be possible to get information, yeah, about the integrated, yeah, light over, well, along the vertical lines, yeah. So for the same value of eta, yeah. So we don't get information, yeah, about the other direction. So what you need to do, well, just take a baseline which is perpendicular to the previous one, and then you will get, yeah, complementary information. But you know, you only get information, and this is the demonstration which will be, yeah, in the PDF document, yeah. Well, at one spectral, well, at one angular space frequency, yeah. So if you would like to get very precise information on the extended source, yeah, you should have you should cover in the UV plane, so in the plane of angular space frequencies, yeah, many different baselines having different length orientations, and then you could, yeah, by applying the inverse Fourier transform, yeah, recover exactly, yeah, the very detailed intensity distribution over the surface, over the source, yeah, with an angular resolution, which would be equivalent, yeah, to, well, the length of the baselines, yeah, that you are using, yeah. So you'd like to get information, yeah, well, at the very high detailed levels, so you will use very long baselines, and then also you would like to get information, yeah, at the small scales, yeah, for which you would just need, well, over a large scale, excuse me, for which you would only need a very small baselines, yeah. Okay, did I answer the question, or I mean, was the question something still different?
Okay, she says yes.
Yes. Okay. I hope it's not a shy yes. Yeah. If you are not satisfied, yeah, just get into the forum, yeah, and we may continue, yeah, right, the discussion. But I think the reading, yeah, of the PDF file that will become accessible on the forum, yeah, will help you to see, yeah, what the Wernicke-Van Sitter theorem is, yeah, from a totally different perspective, yeah. More questions, or?
Yeah, there's one in chat by Sudipta Paik.
Yeah. Yeah. Okay, so the question, yeah, probably relates, yeah, to a star which has a Gaussian shape, yeah. And well, the very nice thing here with the Gaussian shape is that if you take the Fourier transform of a Gaussian, yeah, you still get a Gaussian, yeah. Of course, the full width at half maximum will not be the same, and the correct expression, yeah, is given in the lecture notes, yeah. So if your source, yeah, is a very small full width at half maximum, yeah, well, the Fourier transform, yeah, will be a Gaussian with a very wide full width at half maximum, yeah. And well, in the limit, when your star, yeah, becomes a Dirac function, yeah, so which is infinitely small, well, this is a Gaussian, yeah, for which the full width at half maximum, yeah, tends towards 0, yeah. What you would get is a Gaussian which full width at half maximum tends to infinity, yeah? And this is the case when the Fourier transform is perfectly equal to 1, yeah? So by measuring, yeah, the full width at half maximum in the Fourier space, yeah, of course, by the relation given in the lecture notes, yeah, you get immediately, yeah, what is the full width at half maximum of the source you're observing. But of course, don't use, yeah, the model of circular disk, yeah, or of, well, a square star, yeah, to model a star which you know can be represented by a Gaussian, yeah. And maybe not, a question could be, yeah, well, do we know cases where the stellar disk, yeah, looks like a Gaussian? Yes. You know, most of the stars, yeah, especially young stars, yeah, may be in rapid rotation, and their shape, yeah, then gets elliptical shape, yeah. And there are nice examples in the literature, you know, for which some of the bright stars, yeah, have been observed with an interferometer and shown, yeah, to be ellipsoidal or elliptical in shape, yeah. So did I answer that question? Yeah, so in the next lecture, lecture number 7, well, it is essentially demonstration of the fundamental theorem, yeah, which is something marvelous, yeah, which says that the distribution of the complex amplitude of the electromagnetic field in the focal plane of an instrument, yeah, is simply the Fourier transform of the distribution of the complex amplitude in the pupil plane, yeah. And so, I mean, this requires, you know, some concentration to understand the demonstration. I hope, I mean, you'll be able, yeah, to go through it, yeah. There are many hypotheses, yeah, series of assumptions at the beginning that you will read, yeah, that, for instance, your system must be free of aberration, etc., etc. And then what we will do, yeah, we will apply this fundamental theorem to the case of an interferometer consisting any longer of two point-like apertures, but finite apertures, yeah, represented, yeah, by telescope, real telescopes, yeah. So this will enable us, yeah, to abandon, yeah, one of the restrictions we had, that we were still assuming until now that the interferometer was composed, yeah, of pinhole apertures, yeah. So this will be the reason why we first demonstrate the fundamental theorem and then make applications to it, yeah, make applications of it, yeah, to different cases, yeah, even to the case of a single aperture telescope, yeah. And it is the application of this theorem which will enable us to demonstrate that the dot of light you observe from a very distant star, which is point-like, yeah, is an airy disk, yeah. So it is the same theorem, this same theorem, yeah, which allows you to find, yeah, the shape of the airy disk. So I don't see any more raised hands. Of course, I mean, the best advice I can give you, is really to play with Fourier transform, apply to very simple cases, Well, the most simple case, of course, is the door function, because then you get the sin function, and when you have a good handle, on that case, then you may go ahead, with a more complicated case, I think the most complicated one is one when the source being observed, is a circular disk, because as you know, the end product, is a first order Bessel function, But well, it's kind of fun, to do it once, because as I said, this allowed us, to tackle the case, of a circular disk for a star, and it will also enable us, to derive the expression of the Airy function, for the case of a telescope, which is a circular aperture.
Okay, Jean. I was wondering, you said a more accurate model for the intensity of a star is one where we include the limb darkening effect as well, right?
Yeah, correct. Yeah.
Is that usually modeled with two circular disks of different sizes? Can it be, or is there a better option?
So can you repeat the end of your question? So is this modeled with?
So we know that for a uniform circular disk, the visibility is going to be a Bessel function.
Yes.
I was wondering whether the limb darkening could be modeled as essentially a ring that is of a slightly lower brightness. So instead of a ring, which would be equivalent to taking a larger disk of lower intensity and a smaller disk of higher intensity and just add these intensities, normalize it, and then you get, it will be still a complicated function of Bessel functions, but is that how it's done, or there's some other?
Yeah, you're perfectly correct. You're perfectly right. That we will see, well, when applying this fundamental theorem, we will consider the case of those rings you were referring to, and just, you should just consider that, well, a stellar disk, consists, well, central disk, small area, surrounded by an annular ring, another one, and still another one, and we'll have the right expressions, to represent this kind of model consisting of many layers, More you're putting rings, more you get parameters, of course, and more you need, visibility measurements to constrain your model, but then you are able, to get well, information about the limb darkening effect, And in fact, the limb darkening effect, well, the signature, is mostly present, in the secondary maximum, So, we have a first maximum, then we go to visibility 0, then it increases again, but slowly, and goes to a second minima. And it is, in the second side lobe, that we get most of the information about the limb darkening, But the approach you suggested, is perfectly right and correct, and a good way to carry this experiment,
Okay. So I assume if you're using so many different rings, at that point, the only way to go from intensity to visibility is numerical methods, right? You cannot have an analytical expression.
No. Well, this will be analytical expressions, but still, you will make a least square fitting, of your observations, with respect to your model, which is represented, analytically still, but with many scaling parameters,
Right.
Yeah. Very good question. Yeah.
Sure. Suman, if you can unmute yourself and ask.
Hello, sir. Sir, In normal case, spectra of a star get broadened due to rotation. Can you hear me?
Yes.
Okay. Broadened due to rotation. So is there any kind of behavior we can see in the interferometer due to rotation similar to spectra? Like, this is totally unrelated, but I'm just curious to know.
Yeah. So, well, did I understand correctly your question that whether we are able, yeah, to see this rotation effect, yeah,
Yes, yes, yes.
from interferometric observation? Yeah, absolutely. So not only, yeah, well, people were observing, you know, fast rotators, but they could get, yeah, spectral line information, yeah. So I think they were observing, yeah, some of the bracket lines, yeah, in the near infrared due to hydrogen, yeah, and they could see, yeah, radial velocity effects, yeah, due to the rotation, yeah, and matching perfectly, yeah, the elliptical shape. They were able, yeah, to reconstruct, yeah, from the visibilities and from the phase information, yeah. So absolutely, yeah, you may very, very well constrain, yeah, these fast rotators, yeah, for getting information about the projected shape on the plane of the sky, yeah, and in addition, seeing radial velocity effects, yeah, between the edges, yeah, of the projected ellipsoid. So this was absolutely down, yeah, well, a few years ago, yeah, on several bright rotators, yeah. So this shows, yeah, the level of details, yeah, you may get, yeah, for stellar physics, yeah, using interferometers, yeah.
Thank you, sir. Thank you.
There's a question in the chat which I don't understand which equation he's referring to. There seems to be in the denominator some pi t minus z.
Yeah. So probably it's about, so thank you, Desh, for your reply to the question. Yeah. Yeah, so in the beat phenomenon, yeah, you have, of course, a modulation, yeah, of the amplitude, yeah. Even when you remember the experiment we did, yeah, with simulation, yeah, of sounds, yeah, at two different frequencies, yeah. And we could hear, yeah, modulation, yeah, in the amplitude, yeah, of the intensity. So it's the same with the light, yeah.
I had not answered his question. I just reminded that he had put it up. So now he has repeated it in the chat again. So you can read it.
Yeah. Yeah, so well, I don't know, yeah, if my explanation before is sufficient, yeah, but you remember when we made the experiment, yeah, with the simulator of sound, yeah, we were emitting two waves, yeah, with a frequency difference of 1 hertz or 2 hertz, yeah. And then we could, so I think it was 700 hertz, yeah, and 701 hertz, yeah. And then we could hear, yeah, modulation with an amplitude, yeah, with a frequency of 1 hertz or 2 hertz, yeah. And so, indeed, yeah, it's well, just the result of the beat phenomenon. And I'm not sure, yeah, I perfectly understood. What is the question. Did I answer the question or not?
So his question is whether, does that mean that the amplitude attenuates with time because it has that denominator?
Yeah, well, it does.
Difference.
It's a basically sinc function description describing the level of coherence. And in sinc, you know, there is an oscillatory component, which is the sine, and there is a 1 upon x like component, which is the damping. And so you will find that with progression of the coordinate where the coherence is being assessed, which is described by this sinc, you will find 1 upon the coordinate value will describe the fading, and the oscillation will still continue with the sinusoid component. So yes.
Yeah, of course. I mean, but since, you know, the waves are emitted continuously, yeah, well, your hearing, you know, this phenomenon, yeah, continuously as a function of time. So, well, there is attenuation, but then the signal comes up again and decrease and comes up again and decrease, yeah. So don't be afraid that, you know, the light intensity will vanish. No, I mean, it's a continuous phenomenon.
Right, so the new sync distributions are being created just because it's continuously being superimposed.
Yeah.
But if you have a short-lived beat phenomena, it would attenuate in this form, right?
Yeah.
Okay. Hope that's clear to you, Zhenghui. Any other questions?
Yeah. So if not, yeah, remember, yeah, to read, yeah, several times the demonstration, yeah, leading to the main result of the fundamental theorem, yeah. And because well, it's wonderful, and we are going to apply it, yeah, to many cases. And again, yeah, it calls up on the Fourier transform, yeah. So during this week, yeah, if you may find some time, yeah, to practice, yeah, the Fourier transform, yeah, applied to different analytical function, yeah. And yourself, you may think about new cases, yeah, why not, yeah. Well, a very nice case, yeah, to apply the theory is a case of a double star, yeah, having well, a flux ratio which is not equal to 1, of course, but which orientation you don't know in the sky, yeah. So can be well, if this is a, if this screen is a sky projection, yeah, you don't know how the binary star, yeah, is oriented, yeah. And the idea is, well, just to represent analytically, yeah, this case and find out, yeah, how many observation would you need, yeah, to infer all the parameters for the binary star system. It means the flux ratio and the orientation and the separation, angular separation, yeah. So you see, of course, you will need more measurement, yeah, with different baselines and orientations. And sometimes when you're lucky, yeah, you need a very few baselines. Sometimes you may get very unlucky, yeah, and need more observations, yeah. But it's nice to try to play during this week, yeah, with the Fourier transform tool applied, yeah, to simple analytical cases, yeah.
So it is exactly 3 now here.
Yeah.
Either we can, if no one else has any questions right now, we can stop.
Yeah, so we reconvene, yeah, on next Wednesday, yeah, with Professor Desh, yeah.
Yeah, the coming Wednesday.
Yeah.
Yeah. See you then.
Yeah, and don't hesitate, yeah, to go to the forum, yeah, and raise new questions, yeah, and well, exchanges between, well, all participants, yeah, and with us too, of course, yeah. Yeah.
Okay.
So
thank you, Jean. Thanks, everyone.
Yeah, so thanks to all of you, yeah, and see you in 1 week. No, see you on next Wednesday. Yeah?
Yes,
Yeah.
2 days.
So bye-bye. Yeah, bye-bye to all, yeah.
Bye.
Bye, Sikia.
Bye.
Bye, Desh. Bye, Rakesh. Bye, everybody.
Bye.
Yeah, bye-bye.